Good morning, folks. So we are going to begin section 10.2. The next two sections actually both deal with very specific types of sequences. You may remember them from Algebra 2, you may not. 10.2 deals with arithmetic sequences, which is a special kind of category or a subset of sequences. So let's just go right into it. So what makes an arithmetic sequence arithmetic? And it's very, very simple. Essentially, any sequence in which each term after the first term differs by a constant amount, that is an arithmetic pattern or an arithmetic sequence. So the set of even numbers, if I start listing and rattling off even numbers, that's arithmetic because the difference between any pair of even numbers or consecutive pair of even numbers would be 2. So it's always the same constant. And we call that constant a common difference. And it's very commonly abbreviated with D in any formula as a common difference. And you get that by simply taking any term and subtracting the previous term. So if I take the fifth term minus the fourth term, in general, the n plus 1 term, take away the n term. That will always result in the same constant difference. So let's work with that as a concept first, and then we'll introduce the formula. So I want the first 6 terms of an arithmetic sequence in which a1, our first term, is 100. And we have a common difference of negative 30. So in this case, obviously, it's a decreasing amount. A common difference can be positive or negative. So a1 was given to us, so we have one of our answers already. And we simply are just going to subtract 30 every single time to get the next term. So a1 minus 30 gives me 70. Subtract 30 again, gives me 40. That's your third term. Your fourth term is going to subtract 30 once more. Your fifth term, we're now in the negative, subtracting 30. And your sixth term is negative 50, subtracting it one more time. So this is how to compute or calculate a list of terms. The actual sequence, of course, is the list of those numbers in order. Okay, and again, notice there's very clear subtraction of 30 going on there. Now, let's work with the formula. So we mentioned in the first section of chapter 10 how we can have a general term, or sometimes it's called an nth term, or an explicit formula. And that is something that I can plug in a value and get out a desired term of that sequence. So if I wanted the 20th term, I would plug in n equals 20. So for arithmetic sequences, we have on the screen right now our general term equation. So if I want the nth term, I start by adding the first term plus the common difference times n minus 1. And again, n is kind of like that specific term in the sequence I would look for. So again, if I wanted the 20th term, n would be 20. So I would add the common difference times 19 plus whatever that first term is. So let's work through an example with this. I want the 9th term of an arithmetic sequence, and I don't know the formula, but I do know my first term is 6, and my common difference is negative 5. So there's a tedious approach where we can literally just start with 6 and subtract 5 a bunch of times until I get to the 9th term. That is 1, exhausting, and 2, if instead of the 9th term, I wanted the 99th term, I would not recommend subtracting 5 that many times. It's just exhausting. And it makes a lot of room for error or calculator buttons getting mishit. So this is where our formula comes into play. So I want A9. I want the 9th term of my sequence. So in the formula we just saw on the previous slide, we're going to use 9 for the value of n. They've identified our first term for us, 6, so that's a1, and they've even given us the value for d, which is negative 5. So we have everything we need to figure out a sub 9, which is in the formula the an term. So simply, carefully uh, simplify this example or simplify this expression, excuse me, and you end up with a negative 34, which pretty straightforward and also pretty reasonable that if I start at 6, but I'm decreasing by 5, I'm going to get negative pretty quickly. So the ninth term here is negative 34. Now, let's see a word problem because arithmetic sequences are probably one of the most common sequences in just real life applications of sequences. It's a very common pattern, very predictable and very useful. So based on a census data, which actually this year we have a census, so these numbers are probably going to very quickly be outdated because we have new information in 2020. But from the 2010 census, we knew in the United States 16% of the population was Latino. On average, that was projected to increase by about 0.35% every year. So because every single year it's going to go up the same percentage amount, even though it's a percentage, the amount of the percentage is the constant. So this does represent an arithmetic sequence. So what we first want is a formula for the nth term of the arithmetic sequence that describes the percentage of the US population that will be Latino n years after 2009. So we start with our general form for an arithmetic sequence. We were given a bit of information. For example, we have the first year after 2009, aka 2010, we have the percentage of the population. We also know that the common difference, 0.35%, is what that pattern goes up by every single year. So we have A1 is 16 or 16%, and that represents the year 2010. Keep in mind, we're pivoting from 2009. So 2010 is 1 year after 2009. That's why it represents the first term. And of course, as mentioned, D is 0.35%. So we can plug that in, excuse me, um, and simplify. But you're going to notice that an arithmetic sequence, once you distribute this 0.35 to both the n and the -1, um, you're going to always combine a few like terms, and you should end up with some type of linear equation, which again makes sense because linear equations have constant slopes, constant rates of change, which is kind of similar to having a constant difference. So this is our formula here, 0.35n plus 15.65. Now that represents n years after 2009, the population, the US population that is Latino. So let's kind of use this formula now because it's one thing to have a formula. Now we can actually use it to make a prediction. That's what these are. These are predictions when you're using data. If it was a hard sequence like we were using in the first couple of examples, we would be able to accurately say this is what this term is. This is a projection, so it's a prediction. When we want to know using our formula, what percentage of the US population is projected to be Latino in 2030? So that's actually a nice pivot here. That's the next census from 2020. So simply put, we subtract 2009 from 2030, so that would be 21 years after 2009, and that just gives us the n value to plug in. So simply replace n with 21, simplify this, and you get 23. So this predicts about 23% of the US population is projected to be Latino in 2030. So this is a very thorough, very detailed word problem for an arithmetic sequence, but it's a good example all the same. We're going to spend one more day working with these and probably a little bit of a mini lesson on the finale, kind of summarizing both 10.1 and 10.2 before we talk about a quiz. Probably, I'm thinking Tuesday next week, a quiz on 10.1 and 10.2. In the meantime, there's some homework posted on the course page for section 10.2. Take a look at it, reach out with any questions you might have, and of course, enjoy your weekend.